Okay, so this is the last lesson of the chapter, and then tomorrow we can review and test this Wednesday. So, okay, let's talk about factoring a little bit, right? When we factor something, basically, like let's pick a basic one, right? We factor it and it turns into x plus 3, x plus 2, right? So basically what we've done is we've changed this, we've broken it down, right, into two simpler functions, right, into two simpler expressions. So from this quadratic into two simpler ones that when you multiply give you this, all right? What we're going to do today is a similar thing, but with adding and subtracting rational expressions. Okay, so so rational functions can be written as the sum of two or more simpler rational functions. These simpler rational functions have constants as the numerators most of the time, and their denominators are a power of a linear factor. So basically the denominators are going to be as simple as we can make them. They're either going to be a linear term like x plus 2 and then x plus 2 squared, x plus 2 cubed, or it's going to be something that can't simplify anymore like x squared plus 1. Okay? All right. When we do that, this process is called decomposing something of a rational function into two partial fractions. So decomposing into two partial fractions. And just like here, we see that this gets broken down into two simpler binomials. This one here, right, this rational expression, x plus 3 over blah, 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 gets decomposed into two simpler fractions that when added together give you this more complicated one. All right, so that's what we're going to do. We're actually going to start with that one and we're going to see how that works. I've broken this down into different cases of the problems that you're going to see. The first case is if you have a denominator with linear factors. Okay, so we're going to rewrite this. And, oh, you know what, actually, I'm just going to factor off the first thing here. So how does that factor in the denominator? X minus 5, x plus 4. Okay, so this is the case with the linear factors in the denominator, right? So how many factors are in the denominator? 2, right? You have an x minus 5 and an x plus 4. Okay? However many denominators, however many terms are in the denominator, that's how many fractions you want to split this up into. Each one of the fractions gets one of the denominators. And do you see how now if you're going right to left, if you were going to add these, the common denominator would be x minus 5, x plus 4, right? So we're just like breaking it up. Now, the numerators of this are going to have one less degree than the denominator. So if this is a linear function, then the numerator is going to have x to the power of 0, so it's going to be a constant, right? So for now, we're going to put placeholders for those constants, and we usually, do, capital A, capital B, and then if there were more, it would be C, D, E, F, G. Okay, now, at this point, there are several ways to do this. What we're going to do is we're going to multiply by the LCD. In this case, the LCD is x minus 5, x plus 4. Okay, so here we get x plus 13 is equal to a times x plus 4, oh bless you, plus b times x minus 5. All good there? Okay, next, continuing here, we're going to solve for a and b. Okay, so here's the fun part. Here's how we do this. There are there are like a million ways to solve this. The most fun way is, here's what we do. You basically want to solve for A and B. So what you can do is you can plug in values for X and see what you're going to have left. What I start with are values that are going to make each of these binomials 0. So for example, what makes this 0? -4, and 5 makes this 0. Okay, so why don't I first plug in a 5? So x equals 5. Yeah. No, you can for the purposes of solving, because the rational function temporarily went away. Okay, so here, okay, so that's going to be 5 plus 13 equal to a times 5 plus 4 plus b times 0. Okay, so now the 0 went away. So what I have here is 18 equals 9a, and then a is equal to 2. Okay, good. Next, I plug in x equals -4 to the original function. -4 plus 13 is equal to a times 0 plus b times -9. So -9 equals -9b. So b is equal, no, positive 9. So b is -1. Okay? So now I have a equals 2 and b equals -1. At this step, we could really have plugged in any number we wanted. And then if the a's and b's didn't go away, then we would have like a system of equations. But the wisest choice is to start with what makes each of them 0. So now that I have a and b, then I can rewrite my entire function. So x plus 13 over x minus 5, x plus 4 is equal to a, which is 2 over x minus 5, minus, right, because b is -1, minus 1 over x plus 4. All right? So now, a few things. This is how it's usually written. Formally, it's always like, okay, you write the original equal to this plus this. I'm not going to make you copy over the original every single time. So for the answer, just writing like the right-hand part is okay. That's number one. Number two, what if somebody switched the order here? You did x plus 4 and then x minus 5. So, you know, this one would get the B, this one would get the A. It really doesn't matter. In the end, it's all going to match up. The term with the x minus 5 is going to end up with the 2. The term with the x plus 4 is going to end up with the -1, right? So it doesn't matter if you switch them around. All right, questions? Okay, let's move on. Okay, what if you have an improper fraction? What does it mean to have an improper fraction? That's if the numerator has a degree equal to or greater than the denominator. So for example, what if you have like, you know, x squared over x squared, or if you have x cubed over x squared, right? In that case, before you start the process of this, you have to first use long division to rewrite the fraction as quotient plus remainder over divisor. Then you do your partial fraction decomposition on this. Okay, too many words. Let's just do one. Take a look at this one. The degree on the top is a 2. The degree in the bottom is a 2. That means those two are, it's an improper fraction. So first I'm going to use a little bit of long division. Whew. We missed that, don't we? Yeah. I was just saying the other day, I wish there was a long division problem I could do again. Okay, so divide this by this. What do we get? -2. -2x squared plus 2x, right? And then what am I going to do? I'm going to change the size here. Let's combine them. You get 7x minus 4, and we're done. It's not going to take too many steps. Usually one step is all it takes, right? 1 or 2 steps at the most. You know you're done when this remainder has a lower degree than the divisor, all right? So what does this turn into then? This turns into -2 plus 7x minus 4 over x squared minus x. Okay? Now you're just going to do the yes on this one. So remember, it's quotient plus remainder over this. Yeah? So now you're going to decompose this. All right. So let's copy that down here. 7x minus 4 over x minus 1. Does this follow the same case as before? Yeah, you have linear factors. So again, I'm going to have 1 plus another 1, x minus 1. I do a and b. I'm going to multiply by the LCD. So I get 7x minus 4 is equal to a x minus 1. Don't distribute here, right? Because it doesn't help you if you do. Okay, so first I'm going to plug in x equals 0 because I can. So I get -4 equals a 0 minus 1 plus b times 0. So -4 equals a equals 4. Yep. So what else do I plug in? Right. So 3 equals a times 0 plus b. Oh, how cute. B is just 3. Okay. Now, here's what students always forget, right? So I'm going to write the whole function again one more time. -2x squared plus 9x minus 4 over x squared minus x. Now, this is equal to, first, the -2 from our long division plus, what do I have? 4 over x. Right. All right. Huh? To the right? I mean, I guess convention is, I guess in the beginning, it really doesn't matter at all because this is all going to be used in like other problems later. Yep.
Does it matter? Put the 4 on the other one? Or?
Yes, it does. Yes, it does matter. So a goes with the x, right? So whatever you get for the a, 4 goes with the x. Huh? Because when you started, you labeled a with x, you labeled b with x minus 1. Now, had you switched it, that's what I was saying before. Had you switched it, suppose you write x minus 1 first and then x, and now you do a and b. This time, your a is going to turn out to be 3. Your b is going to, and then it all works out. Trust the math, man. Trust the math. It's bigger than us. The math knows, right? Yeah, the math knows it's bigger than us. Okay, so second case, what if you have a denominator with repeated linear factors? Okay, what does that mean? This is exactly what it means. If the denominator has a linear function factor that's repeated n times, the partial fraction has to include, okay, so this is what we mean. Take a look at this denominator. You have x, but 3 times, right? This x cubed, it's like in the denominator, you have x times x times x. And then you have, x minus 1, x minus 1. So total, how many terms do you have? 3 x's, 2x minus 1's, 5 total. That means you have to have 5 total fractions. And then the denominators, you take the first term, you start with an exponent of 1, and then you build up until this exponent. And then for the x minus 1 squared is what you have. So you start with exponent of 1, you build up until this maximum exponent. Okay? So, let's take a look at this one. So I have 3x squared minus 5x plus 4 over, okay, I'm going to let's see, I'm going to factor this in 2 steps. So let me, on the original, let me factor out an x. And then that factors further, right? What does that factor into? So x minus 2 squared. So take a look. There are a total of 3 terms underneath. It's x minus 2, x minus 2. So I'm going to have a total of 3 fractions. Okay, first one gets an x. That has a power of 1. That's pretty clear. We're done. This one has an exponent of 2. So first I write it with an exponent of 1, and then I write it again, and I keep adding the exponent until I reach 2. Okay? So now, constants. This gets an A, this gets a B. Nothing new here. Okay? And then this one, look at the term itself underneath. X minus 2 is still linear, so it just gets a C, right? Because it's a linear term that's being squared, right? It's a linear term that's being squared. It just gets a C. So now we're going to do the same thing. I'm going to multiply this whole thing, x minus 2 squared, x minus 2 squared. So I get 3x squared minus 5x plus 4. Okay, you're going to distribute this. So for the first term, I'm going to get a x minus 2 squared plus bx x minus 2 plus cx. Okay, let's plug in x equals 2 first. So over here, when I plug in x equals 2, I get 6 equals a times 0 plus b times 0 plus c times 2. Here? Well, these cancel.
Oh, wait. I'm sorry.
That's okay. Okay, so then what else can we plug in? 0. So I get 4 equals a times negative 2 squared plus b times 0 plus c times 0. 4 is 4a, a is 1. Okay, now I need another one, right? Now I need another one. Okay, I'm out of things that make this 0, but I was never just contractually tied to just those numbers. Really, I can plug in whatever I want. I can plug in 157.4 if I wanted to. But I'm not going to do that. I'm going to plug in x equals 1 instead, right? Because I can. So let's plug in an x equals 1. And I get 2 here equal to a 1 minus 2 squared plus b times 1 minus 2 plus c. So 2 equals a minus b plus c. Oh, but I already know what a and c are, right? So 2 equals 1 minus b plus 3. B is how much? This is a plus 3. So let's see, negative b, this is a 4, b is negative 2. Right? Oh no, positive 2. Huh? Is it a positive 2 or a negative 2? Positive 2, yeah. Okay? So, did I do that right? Okay. So, now I got A, B, and C, and I can just rewrite them as, let's see, A was A over X, so 1 over X, plus 2 over X minus 2, plus 3 over X minus 2 squared. Okay? And if you find yourself with a little bit of time to spare and you're like, Miss Malik, and I really don't believe that that equals that, well, you know what? Just go ahead, do common denominator and add them, and you'll see that it does, in fact, add equal to that. If I were to take the common denominator here, what would it be? X x minus 2 squared. So x minus 2 squared, and then magically it all adds up to that. Isn't this the coolest thing you've ever seen? I mean, seriously, how cool is this? Did you ever think in your life you could take a function like this and then decompose it into the functions that made that? Why aren't you guys as excited about this as you should be? This is like, oh my God, you guys are lame. You're being lame. You guys are being lame. This is the most exciting thing since, like, I don't know, sliced bread. Okay. All right. Fine. Have you heard that expression before? Okay. All right. I'm not. Okay. All right. Okay, let's kick it up a notch. What if you have denominators with quadratic factors that you can't factor? Well, remember how we said whatever the denominator is, the numerator has to have one less degree? What if the denominator is quadratic? Then the numerator has to have a linear term. Well, what is our favorite form for a linear equation? It's y equals mx plus b. Okay? Okay, but why mx plus b? Because some person decided that it has to be m and b? What if it was, I don't know, some other letters? Can I make it like ax plus b like that? Of course I can. Or I can even make it like cx plus d, right? Okay, so take a look here. You have x, and then you have a factor x squared minus 1 that does not reduce. So that factor x squared minus 1 has to have a linear term bx plus c. Okay, so let's take a look at this one. Oh, last problem of the chapter. All right, so x cubed minus x over x squared minus 3 squared. Okay, there's nothing to factor here. There is a term that has a squared. So I'm going to get two fractions. First, it's going to be the parenthesis to the power of 1. Then it's going to be the parenthesis to the power of 2. And if this was x squared minus 3 to the power of 3, I would have had another one to the power of 3. Okay, so now here, this is quadratic, so it gets a linear term, ax plus b. This is still quadratic. It gets a linear term. I already used a and b. Now I do cx plus d. And if you had another one, you would do ax plus g and then an f and then whatever, okay? Okay, so we're going to do the same thing. Multiply this by the common denominator. Okay, so x cubed minus x is equal to ax plus b times x squared minus 3 cx plus d times x squared. Oh no, that's it. Okay. Now, I'm going to show you how to solve this a different way. There are always more than one way to solve something. I'm going to show you how to solve it a different way because that's a technique that I want you guys to be introduced to as well. All right? So here's what we're going to do. We're going to FOIL this side. Okay? So I'm going to get, bear with me here, ax cubed minus 3ax plus bx squared minus 3b plus cx plus d. Now we're going to do something. We're going to group by powers of x. So all the x cubes together, all the x squares together. So just rearrange this, okay? So x cubed minus x equals ax cubed plus bx squared minus 3ax plus cx, right? Those are the two x's that I put together, minus 3b plus d. Okay, now this is ax cubed, that's alone, bx squared, that person's also alone. Here, I have two terms with an x. What I'm going to do is I'm going to factor out an x, okay? So I'm going to get plus, in parentheses, negative 3a plus c times x. Right? I just factored out an x and I wrote it here. So now what happens is this is the x, the coefficient is this guy. All right? And then plus these two they have no x's, so those are the constant term. So imagine if I had 5x cubed plus 3x squared plus 4x plus 2, right? This is the constant term, that's the coefficient. Okay, now this is my favorite thing to do. And in like college, in the math, there's, places where you have to apply this. So here's what you do. You have to compare coefficients of like terms. And you have to set them equal to each other. So take a look here. This is the x cubed term. What's the coefficient? A. Here, what's the coefficient? 1. If those two are equal, that means their coefficients have to be equal to each other. So I say 1 is equal to A. Now I've solved for A. Okay, this is the x squared term. Here, there is no x squared. That means what's the coefficient of the x squared term here? 0. So I say b is equal to 0. Here, this is the coefficient of the x term. What is it on the left side? Negative 1. So I say negative 1 equals negative 3a plus c. And then this is the constant term. To the left, there is no constant term. That means it's equal to 0. So negative 3b plus d is equal to 0. Do you see how here you've got equations, multiple equations with multiple unknowns? This is why this is in the matrix chapter, is because you can potentially, in the beginning, do all this with matrices, but we're not gonna because it's an extra complication. These are more fun. Yeah.
Where do you get negative 1
For here? Okay, this is the coefficient of the x term. Where is the x term here? Here, what's the coefficient? Minus 1. So now, every term you have, okay, let me finish this. So negative 1 equals, guys, negative 3 times 1 plus c. So what's c here? Right, and then negative 3 times 0 plus d is 0, so d is 0. So let's write all this up. So x cubed minus x over x squared minus 3 squared is equal to ax plus b, right, is what we had. So 1x plus 0 over x squared minus 3 plus cx plus d. C is 2x plus 0 over x squared minus 3 squared. And that is what you get. Okay? So it could have been that, this looked a little different. Now on the homework, I have one that goes to F and stuff. But that's okay. That's fun. Okay? All right, so let's go ahead and start on homework. Oh, you have 15 minutes. Oh my God, you guys can do so much of the homework. All right.